All right, good afternoon. Here we are for another lovely session of ENGR 2302 Engineering Dynamics. Today we'll be working through some material from chapter 15 of the text. So let us begin. Today I'll be looking at the kinematics of rigid bodies. So today I'll be looking at the kinematics of rigid bodies. All right, kinematics of rigid bodies. So kinematics of rigid bodies. So first of all, I want to do a bit of a roadmap to where we've been. So the first thing we looked at was individual particles. And a particle, of course, is something with no length, no width, no breadth, etc. It's a point. Might have mass, etc., but it's just a point. But in kinematics, we're not considering masses. We're just considering rotations and displacements and things like that. We're just considering behavior, position behavior, acceleration, velocity, etc., but not looking at individual properties, things like mass and weight and things. Well, actually, sorry, not weight. Not looking at things like, kinematics, yes, we're not looking at weight, mass, things like that. But again, we first looked at individual particles. Then we looked at systems of particles where you have a finite number of discrete particles, but you're still analyzing them as a system of things, a swarm of things, we might say, systems of particles. And finally, we're moving on to rigid bodies, which are really the logical continuation of a system of particles. So instead of having a large cloud of discrete objects or a handful of discrete objects, we will have a continuum, a single object, a large object made of many pieces, all rigidly joined together. And of course, I would like to define what a rigid body is. And if you have taken me for statics or seen some of my old statics videos or something like that, I define a rigid body as, or maybe in some previous material from this class, a rigid body is an element or body. An element or body that does not bend, twist, flex, or deform any way under load. It can rotate and translate, or translate and rotate, but the geometry is constant. Now, really, this seems, well, on the one hand, this is completely impossible. But on the other hand, this assumption really isn't too bad. So, on the one hand, again, this is completely impossible. But on the other, it's not too bad. So I want to elaborate on this a little bit. So, what do I mean by this is impossible? Well, if you had a material that really could not bend or twist or deflect or anything like that, it would effectively have infinite strength. It would be an infinitely stiff, infinitely rigid material. So that's why something like this is completely impossible. You could apply if you truly had a rigid body, you could have a 1 inch square width of material, a cross-sectional area rod or something like that, and you could hang the weight of the world from that, quite literally, if you had a rigid body. You could have a rotational shaft, a drive shaft or something like that you could transmit an infinite amount of power through. You could do all sorts of crazy things. Actually, my favorite wacky thing you could do with a truly rigid body is you could actually use it to send a signal faster than the speed of light. Because if you study the speed of sound in materials, you find that it relates directly to the stiffness of the material. The more stiff the material, the higher the speed of sound in that material. So if something really were infinitely stiff, it would mean that as soon as you moved the left end of it, the right end of it would move in at the exact same instant. In reality, when you push on the left side of something, the right end of it does not immediately move. It usually moves so quickly that you can't perceive it with your mind. But in reality, there's a tiny delay. A propagation wave of your force has to move from one side of the object to another. But the speed of that wave is basically determined by the speed of sound, or is the speed of sound in the object. So in that material. So if you had an infinitely rigid object, you could actually transmit a signal through that material from one end to another instantaneously in 0 time. So yes, if you had a cable of something and you tapped on one end of it, the signal would propagate all the way through it to the other end instantaneously, traveling faster than the speed of light and thus causing all sorts of problems. Because if you take a physics class, you can learn that can take a certain physics class, you could learn that would allow you to send signals back in time and all sorts of wacky things. So let's not worry about that. Anyway. So on one hand, a rigid body assumption is completely impossible. We cannot have a material that is truly a rigid body. However, in most cases, this isn't really that bad of an assumption. Even when I say something like this, if I look at again, rigid body assumption is completely impossible. Are completely impossible. But the assumption is usually not that bad. Is usually not that bad. So for example, if you remember from statics, when I did shear and bending moment diagrams, or when you did shear and bending moment diagrams in statics, you usually assume that the beam is perfectly horizontal, and you apply a point load P. You're assuming when you calculate that shear and bending moment that it does not deflect. Now, in reality, it would deflect, and in reality, that deflection would actually change ever so slightly how the forces inside that beam are distributed. So the shear and bending moment would actually be slightly different in the curved beam than in the perfectly horizontal beam. But normally you're talking about this delta being so small. You know, delta is often maybe less than an inch, or more likely it might be delta. Usually we limit delta to something like less than or equal to the length over 240 or 180 or something like that. It is very small relative to the length of the beam. So if you have a bending moment calculation that is determined in terms of L, it's really not going to change things that much if the length is off by a tiny fraction of 1%. So again, with the rigid body assumption, I will get a slightly different shear and a slightly different bending moment than I would if I actually did a much more complex, say, finite element model. But really, it's not too bad. You're talking you'll get an answer within a fraction of 1% of what the real value is. And even then, we can keep at, or even the finite element model would have certain assumptions, and we could keep going at this all day. We could add one complexity to another, and to another, keep going down that rabbit hole until we're trying to analyze things on the level of atoms. But anyway, and the same kind of thing happens with rotation. Happens with moving systems. So for example, if I say I have a a rotating shaft or something like that, and I have a drive shaft that is rotating, and the stresses within this, as you learn in the mechanics of materials, are going to be determined by the moment of inertia. And the polar moment of inertia will be proportional, the polar moment of inertia will be proportional to the radius to the fourth power. So if you actually expand the radius of this cylinder, this is a cross-sectional area of a rotating cylinder or whatnot, that, as you can think of it, it makes sense if you think about it, that as this thing rotates, it stretches a bit, doesn't it? That makes sense, right? That if you spin something, just like a pizza, if you imagine like a Italian chef spinning a pizza in the air and making it expand outward, right? Does that make sense? Now the same thing happens for all materials, even aluminum, steel, metals, whatever. As you spin them, they will ever so slightly expand. But usually you might analyze this as if you try to calculate stresses in that material, you may analyze it as a rigid body. And yes, your results would be slightly different than the value that if you try to take into account that slight expansion. But you know what? It's going to be so close that it's not going to matter. It's going to if your design is that precise that a tiny 0.1% increase in stress is going to cause it to fail, you're doing something wrong. What's going to happen is one day somebody's just going to come on and lean against the machine, and this thing is under such tight tolerances that it's going to follow. It's going to explode because one day it was hot outside or something really stupid like that. So we add tolerances to all of our real world engineering problems, and that takes care of all of these really tiny, tiny changes that come as a result of our simplifying assumptions. Actually, in the case of this, that the expansion might actually help you a bit because if you expand the radius, your polar moment of inertia increases, and that actually decreases the amount of stress within the material. So that actually might help you in that case. But anyway. Okay, so let us define kinematics of rigid bodies. So we've discussed what rigid bodies are, and we've discussed what kinematics is in the past. Maybe I'll just bring it all together here. Kinematics of rigid bodies. And this is going to be describing the motion of rigid bodies without considering forces, masses, energy, or momentum. We will only be looking at, we'll only consider position, velocities, and accelerations. Velocities and accelerations. So you can have types of motion that we'll look at. Types of motion. Well, we can have translation, both rectilinear and curvilinear. Or we can also have rotation. And so other types of motion, we can have rotation about a fixed axis. And we will look at all of these. We can have general plane motion. Motion about a fixed point. Or we can have general motion. And we will discuss all of these throughout the next several days. So really these are a brief introduction to, or this is sort of an outline for all of the material from chapter 15 in the Beer Vector Mechanics book. Okay. Any questions on that? Okay. Well, I know some of that stuff may not make a lot of sense now. We will be looking at it now. Okay. So first, let us consider translation. What does translation mean? We could go to translate.google.com, but I don't know if that's going to help us for this. Although you may feel like I'm speaking Greek sometimes in these videos, but hopefully it's not too bad. So consider an object here. Let's see. Consider an object, and I'm going to draw one of my favorite things, which is a potato. I draw lots of potatoes in my classes. And when I say a potato, I mean just a general body. I'm going to draw a object with just a nice vague form. Big purple potato. And consider an object that moves from point A to point B. Maybe we, I don't like labeling that. So let's say I have X, Y, and Z. X, Y, and Z. And maybe initially it was at point A. Point A, and this was RA, vector RA. Then later it moved to point B, and this is RB, RA and RB, and then we have the vector from A to B. RBA, which would be the vector from A to B. Okay, so translation. So a body in translation. So this would be translation. This is motion in a straight line. This is motion in a straight line. And so basically there is no rotation going on if it's under pure translation. And all particles moving in parallel lines. So if you want a good example of pure or reasonably pure translational motion, actually, well, I can think of some different ones. The simplest example, or a simplistic example, would be something like a train. Oh my goodness, I'm going to try to draw a train. This is going to turn out very poorly. Oh my god. Okay. So I have a train, a very crudely rendered train. And thank you. And this is apparently like some 19th century steam locomotive, because that's what we still go around in. Maybe it's one of those trains at the zoo or something. Very serious train. And so we have a train. Now, consider this train. Now, I'm going to ignore the motion of the rotation of the wheels and anybody walking around inside the train and all that kind of stuff. And also the molecular vibrations and all of the little minutiae that you could try to catch me on if you're being a ass or something. But let's just consider the train in a very let's consider the train as a rigid body, just sort of sliding along here. Maybe a sled or something. But anyway, so if I look at a molecule at the wall of one of the walls of the train here, compared to one of the molecules in the wall of the train here, the floor of the train, wherever it is, I can pick one of those atoms, and they're all moving in a straight line together, aren't they? They're all moving in a straight line together. They're just going along the track. They have a motion. Now, I'm ignoring the small things like, actually these can be quite large things, but ignoring the intermolecular little vibrations of atoms and all that kind of thing, and the vibration of parts. And if we really wanted to get into the dynamics of trains, we could go down this rabbit hole quite far. But let's just consider the train a rigid body, etc., etc. Or another example would be if you're just floating through space. If you were flying through, actually that's probably a poorer analogy. Well, I don't know. I guess everything's ultimately curvilinear motion when you think about it. But anyway, so actually, I shouldn't just label this translation. I should label this rectilinear translation. Sorry about that. Rectilinear translation. So if I were considering something. Say I was flying through space, I didn't have any rotation about me, I wasn't spinning or anything like that, I was just sitting still. And if I was just sitting still and it was a spacesuit, And let's say I'm like, I don't know, in interstellar space or intergalactic space, far, far, far from any sources of gravity. So I'm just kind of flying in a straight line. That would be as close you could get, you could probably get to a pure system of translational motion as you could. But even then, it would not be perfect. So that would be one type of translation. And so again, for any two particles in the body, actually, let me do this down here. I think I'll just take up the whole slide for rectilinear motion. Virtual paper is cheap. For any two particles in the body, well, I can say that RB is equal to RA plus R from B to A plus R from B to A. And then if I differentiate with respect to time, R dot B is equal to RA dot plus R from B to A. R from A to B dot equals RA dot. Equals RA dot here. Here. And then also, so VB, V at point B, equals VA. So therefore, all particles have same velocity. All particles will have the same velocity. And then I could also say that here, that if I differentiate again, I would get RB double dot, and the reason this is going to be the same here is because this term here is 0. There may be a vector between A and B, but there may be a displacement vector between A and B, but there will be no change in that. It's a rigid body. The distance or the vector from here to here is not going to change with time. So this term, the R from B to A, the R from B to A dot, or for R from A to B dot, that is 0. Okay, so differentiate again, RB double dot equals RA double dot plus R from A to B double dot, and again, and again, this will come to 0. So that just equals RA double dot, RB double dot is equal to RA double dot. Therefore, AB equals AA, which you may feel like you need after this class. And so, therefore, all particles have the same acceleration.
Which means on first derivative, the R B respect is also equal to 0.
The first derivative, yes. Because if you think about it, just a second, I'll have the same acceleration. Yes, the first derivative of, again, because RBA, or R from A to B, B slash A, I have it written here, is 0 because, while there may be a position there, that's just a position. So I'm holding up a water bottle here, and if I trace a vector along here, right? If I trace a vector along this water bottle, if I throw this water bottle, I don't want to, but if I throw this water bottle, the position of this end and this end are going to change. If I define the corner here as the corner of the room here as my 0, 0 coordinate, the vector from the wall to here and the wall to here, that will change with time. But meanwhile, the vector from here to here will not change. It's a rigid body. The thing is fixed by geometry. And at least if it's purely translating, now, If this thing were rotating as well, then I might get the vector changing, although the magnitude of that vector would not change. The magnitude of it wouldn't change, but the direction of it might as the thing tumbled through the air. Don't worry, I won't throw my metal water bottle at you. That'd be a little mean. So I try to encourage questions, and I find throwing heavy objects is a bad way to encourage questions. So Okay, so that is, and these equations will apply to curvilinear motion as well. And I also will define curvilinear translation. Yeah, why not? Or maybe draw it out. So if you had something, maybe I'll draw another one of my favorite potatoes. Nice purple potatoes, as we always consume. Big purple potato. And so you would have a motion, perhaps something like this. Consider points A and B, and point B. Well, this object may be traveling in a curved path. Maybe it's traveling in a curved path of some sort. Oh, what color should I use? Maybe orange again. But the path traced by, as long as this thing isn't rotating, the path traced by A and B will be the same path. And so these are meant to be parallel lines at each point, so or have the same slope at each point. So again, they will trace the same path in space. Or if I were to draw out their accelerations, they would look something like this. They would have maybe acceleration vectors, something like AA, and then AB, both of them being the same acceleration vector. Now again, if this thing is rotating, that goes out the window, but as long as this thing is only translating, it will not be experiencing any kind of rotation. So all of these will be true. Now, what else? So the other notes. Can anyone think of a good example of curvilinear translational motion? Can anyone think of a good example of curvilinear translational motion? Where something would be translating but not necessarily rotating, but still in a non-straight path.
Those benches on your front porch
Benches on the, maybe. Those would do it.
that swing though, but the ones that actually...
Oh, the ones that keep you horizontal as you swing? Yeah, that might be a good example, like one of those porch benches that swings. Another good example I could think of would be actually, I come back to space a lot. I like space, but I'm a bit of a space cadet. But orbits, planets, things like that. If you have a satellite in high orbit or whatever, if it's not experiencing significant tidal forces. Now, especially if you made a spherically symmetric satellite, like if you just had a basketball or a solid sphere of iron or anything like that, as long as you didn't give it a rotation. So like, in other words, if you actually have objects that aren't spherically symmetric, you can actually get some sort of torques on them in orbits and some sort of tidal effects. But if you had a nice spherically symmetrical object, like a big sphere of steel or something, and this thing was orbiting around the Earth, and this is not to scale, but so say you had let's just draw a nice big Earth. And let's say you had, now this is not to scale, it would actually be worse if this was big. It's good that it's small, because then we can definitely treat it like a spherical system. But in other words, if this thing were rotating around the Earth, and let's say I'm looking at the ball and the Earth from the North Pole, and this thing is going around, and I paint a single stripe on this ball. As this thing goes around the Earth, as long as I didn't give it any rotation initially, it will experience rotation. It will experience a curvilinear translation due to the Earth's gravity, but it won't actually experience any rotation. It will just be like this constantly. The motion around the Earth does not affect the motion of the rotation of the body, as long as it's spherically symmetric. Now, if it's a really complicated shape, you can get some sort of force that tend to torque it in one direction or another. But something like the International Space Station is not by any means spherically symmetric. So it actually does get certain torques that make it kind of want to orbit in one up direction, basically. But if you had something nice and spherically symmetric, like actually a basketball would be a terrible idea. That would pop instantly in outer space. Let's just say like a sphere of iron or a solid. I don't know why you would put a solid sphere of steel into orbit, but I suppose if you wanted to, you could, just to prove a point. And that would be the case. And in fact, they actually sometimes use this for satellites. So if you want your, especially if you have like a communication satellite, now this would not be in pure translation motion. You actually, say you have a satellite that is up in geostationary orbit. And I think we've already defined that before, right, in class, where we say that its time to rotate around the Earth is exactly the same as the rotational period of the Earth. In other words, you put it high up enough that it takes 24 hours to go around. And then that satellite will be at the same point in the sky at any point on the ground. Basically, no matter what latitude you're at, you can just point your satellite dish at one stationary point in the sky, and that bird will always be there. Well, how do you handle rotation? You see, most satellites, a lot of them anyway, they might have their own sort of like communications antennas, right? And you want to make sure that the communication antenna on the satellite always faces the Earth. And the way you do that is you give it a very, 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 very slow rotation. So you make this thing, it's probably difficult to do that, but you just have very, very subtle gyroscopes or whatever that will do that, flywheels or maybe small jets or something like that. And you make this thing rotate so that it rotates around its own center of mass over 24 hours. And so as this thing is going around the Earth, basically as it goes around, that antenna is always pointing toward the Earth because its translation is lined up with its rotation. But if it was translating and rotating, that wouldn't be pure translation. But anyway, that's just some of the applications of curvilinear translation. Okay, so next I want to talk a bit about rotation about a fixed axis. All right, so velocity about a fixed axis. About a fixed axis, and let's look at velocity. Velocity. So if you consider this, let me draw out a potato. Draw another one of my favorite potatoes. And I'll define some axis that occurs through that potato, or through that. The technical term would be a general rigid body, a generic, an arbitrary rigid body, or we can just call it a potato. Just a lump of matter of some sort. It could be more specific, but we'll just keep things nice and non-specific for our analysis here, because we're talking in very general terms. So let us say that we have a set of axes, x, y, and z. And maybe in this case, I'll define them like so here. X, maybe y and z here. X, y, and z. And consider point P. Consider point P here. And this thing is going to be rotating about this axis here. A, and let's call this point here. Oh, and let me extend this one down a bit. basically I'm aligning my coordinate system with my axis of rotation. So this is going to be point A, maybe A prime here, A prime and A. So I have rotation. Consider rotation of a rigid body about point, sorry, not about point, about axis AA, or AA prime. AA prime. Consider rotation of a rigid body about AA prime. And let me label a few more things. So I'm going to have point P here, and I'm going to have some, again, I'm going to have rotation about this axis, so kind of like this, rotation like that. And then point P will trace out a circle about this axis, like so. And there's going to be point B here, which is going to be the perpendicular location along axis A. So this is the point B is the perpendicular. And a few other things. I know this is getting very crowded. This is going to be angle phi. So at some given time, point P, well actually it will always have a, about the origin, it will always trace angle phi. About the origin, it will always trace angle phi. But through time, it will change angles, it will have a certain angle theta measured from the y-axis. Some angle theta. And I think that's about what I need to cover. So, let us discuss a few of these things. Velocity vector V is going to be equal to dr dt of the particle P. So I'm basically taking one particle out of the rigid body and analyzing its motion. Of the particle P is tangent to the path. Tangent to the path. So V is going to be my translational velocity, or not translation, I shouldn't say translational, linear velocity of this point, of the path with magnitude, let's say V equals ds over dt. And if you've seen S before in this class or others, of course S means arc length. So delta, or delta S, is going to be equal to BP. That would be the radius, the distance from B to P. So the distance from B to P times delta theta. So in other words, just R theta. Or this is equal to R sine of delta phi. R sine phi here. Oh, actually, let me say this here is R. R is not the radius. R is the distance from the point itself, from the origin itself to point P. But I want only the distance here from B to P. That is R sine phi times delta theta. Times delta theta. And this is equal then to, again, there's that. And so then V, the velocity, is equal to ds dt. V equals ds dt equals, oh my goodness, that's very poor writing. Ds dt is equal to the limit as delta t approaches 0 for r sine of phi. R sine of phi from delta theta delta t equals r phi dot sine phi. Phi dot sine, theta dot sine phi. R theta dot sine phi. All right. And I can do another extension of this. I also wanted to define angular velocity once people finish some writing. Okay, so the same result is obtained from well, V is equal to dr dt is equal to omega cross r, where omega equals omega k equals phi dot k, phi dot k equals the angular velocity. So you probably remember omega from your high school physics class, or also from your university physics class. Well, hopefully anyway. I don't know how some of you might have taken even your university physics quite a while ago, depending. But again, omega is your angular velocity. It is measured in radians per second. So hint, hint, you might want to always check to make sure your calculator's in radian mode, etc., especially on exam time. Always keep that in mind. Some people always flub that up, but such is life. So that's your angular velocity. Well, when it's just omega, it's going to be a scalar, would be a scalar. But if we want to actually make it a vector, I would need some sort of like omega k. That would be your vector, essentially. Your vector. Okay, and here, and notice, let me go back here. Notice the, what direction does it point? Let's think about this. What direction does that vector point? Let me draw this out. So, yeah, it was along the z. So if I had the z-axis here, if I think I had the, like y, x, and z. If I have a rotation like this about a point, something kind of like this, well, I want to use the right-hand rule. So if you remember your right-hand rule, if I kind of twist my, I can't portray this on the video, unfortunately, but if I use my right hand and trace a curl around the path of motion, my thumb will point in the direction of that vector. So when we say rotation has a vector, well, at first that seems kind of weird. A vector is pointing in one line, in one direction. How can something that is going in a circular path, how does that have a vector? That doesn't make sense. Well, as you remember from physics class, or hopefully remember from physics class, what that means is when I say something has a, when something has a vector, or when rotation has a vector, or when I say that something's rotational momentum has a vector, what I am talking about is, I am talking about basically whatever plane, the circle that it's rotating in, the normal vector to that. So if this rotational path here must exist in a certain plane, right? And I'm looking for the normal vector, I'm looking for the vector normal or perpendicular to that plane. Or in other words, I am looking for the vector of the axis of rotation. So maybe I could actually write that out here just for emphasis. The vector of the rotational velocity describes either just the right-hand rule, if you want to think of it that way, the vector of the axis of rotation, the rotational axis. Or we could say that it is the normal line, or the line normal, to the plane that contains the path of rotation. So I could think of all sorts of ways to define what this vector actually means, the rotational path. All of these are basically, I'm not saying it can be this, this, or this. I'm saying that these three things are functionally equivalent. These are the same thing, basically. Just different ways of mathematically stating the same thing. Okay? Here. And the acceleration, I'm going to move on to acceleration, angular acceleration. But I won't go in depth about the angular acceleration vector because it's really the same thing. It's the same idea. Or in terms of, I won't go into what that vector means. In terms of the direction of it, it means the same thing. Okay, so let us look at rotation about a fixed axis, acceleration. Rotation about a fixed axis. What if it's accelerating? Acceleration, and eventually we'll get into torques and things like that, but for now we're just looking at kinematics. So we're not worrying about what causes the acceleration. Now, of course, we know from physics class, or hopefully know from physics class, that it is a torque that's going to cause that acceleration in relation to its moment of inertia, etc., etc. But anyway, so let's continue on here. Rotation about a fixed axis, acceleration. And if I take that same thing and differentiate, if I take the previous expression and differentiate, just expression and differentiate. Well, I'll end up with A, acceleration vector, equals dv dt, equals d dt of omega cross r. Omega cross r. This is then equal to d omega dt cross r, d omega dt cross r, plus omega cross dr dt, equals d omega dt cross r, d omega dt cross r, and this is based off of essentially a really kind of a chain rule or product rule type thing. D omega dt cross r plus omega cross v. All right. Now, I want to define what d omega dt is. I want you to define a new quantity. And again, this should seem familiar from earlier physics classes. D omega dt is going to be equal to alpha, which is angular acceleration. And this is equal to alpha k. Now I'm going to try very clearly to make my alphas very different from my k's. So I always try to exaggerate the alpha and it ends up looking like a Jesus fish or something. But anyway, I try to make my alphas very distinct from my k's, or alphas very distinct from my a's, sorry. So this is going to be equal to omega dot k equals theta double dot k. Okay? All right, so we've now defined the angular acceleration and see what that means. Let's see. All right, so here, and then acceleration can be thought of as the combination of two vectors. The acceleration of p thought of the combination of two vectors, they're thought of as the combination of two vectors well, A is equal to alpha cross R plus omega cross omega cross R, or omega cross R. Isn't that fun? Omega cross R. Lovely. And alpha cross R is the tangential component, the tangential acceleration component. The tangential acceleration component and omega cross R. Omega cross R, this is the radial acceleration component. So this is not an alpha, this is an A. This is the overall acceleration of the particles. So if you think about it, if something is going in a circle, traveling in a circle, there is both a tangential component and a radial component to its acceleration. If it's traveling at a constant magnitude velocity and it's just changing direction, all you would have is the radial. But if this thing is accelerating, or if this is spinning faster or spinning slower, there would also be a tangential component to that acceleration. All right, so maybe I think I'm going to work a little bit more on here. Let's say, actually, I think we might take a break there, come back and look at some more material. All right, let's take a quick break, come back and we'll look at some more of this.